Before we start this, I always like to say this is my favorite and least favorite lecture to give. It's my favorite lecture to give because it kind of gets out of the general vein of the sorts of lectures you hear from me where we talk about here's some stuff that you probably don't really care about that too much, and here's the details that go along with that, and then we try to put that into practice. This lecture will be more sort of how did scientists use the knowledge that you have right now to solve a problem, right? So it's a scientific success story, and really has made a huge impact on not the Earth overall, but people living on Earth, right? It really solved an extremely difficult crisis that people were working through using right scientific nature and scientific methods and all that, but also working through the politics and getting stuff done essentially, right? So I like to tell the story because it really helps you see that there's a possibility for that to occur. That's probably why most of you guys are in a science major, right? You want to make a lasting impact on, the Earth or at least right society or something like that. So you have these lofty goals. This is a story about how that actually happened. It's my least favorite lecture to give also because it means the class is coming to an end and you guys are all moving on to other things, and it'll be right. It's always a kind of a sad thing to think about the ending of something, but it's always the beginning of something better after that, right? So hopefully you've gotten. I know this has been a very bizarre way to take Chem 1A or any other classes you've got this semester, but hopefully you can see here sort of where you could go with the knowledge and the skills and the critical thinking you are hopefully developing over the last 3 or 4 months. So just to kind of set the table, right, what we're going to do here is I'm going to talk to you about some things that happen in the atmosphere, one particular success scientifically, at least story that we're going to go through. And as you probably are here for, there's extra credit involved with watching and kind of absorbing a little bit of information from this lecture. So there'll be a tiny little assignment to do at the end of this lecture here for 1 point of extra credit added to your final exam score. And then on the final itself, there will be 2 questions about 2 concepts that come from this lecture. I will make it extremely obvious what slides those come from. So if you wanted to kind of just listen, absorb, listen to the story, and then whenever I go, hey, come out of your coma for a second, this is what I want you to pick up from this. And that'll be what I'll make it very obvious what the question will be. Will be. So there'll be 2 more points available from this lecture that'll go toward your extra final exam total. Okay, so here's a picture, a very complicated picture of the atmosphere and a bunch of stuff kind of overlaid onto it. So I'm not sure if it's going to come through. I'm going to use the mouse arrow in lieu of my laser pointer, so I'm hoping it'll come through on the video. But anyway, over here you see basically from the bottom of this axis here tells you how far we are up above the Earth's surface. There are 5 different areas of the atmosphere, right? There's the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. On the very far left is the relative composition of the gases that's there, right? We have a lot of stuff going on in the first 80 or so kilometers, and then it kind of gets pretty sparse up here. So not that you ever will find yourself, but if you were, let's say, floating on top of the Mir space station or where you're getting your cell phone coverage beamed to you, and you stuck your head outside, there's really nothing for you to breathe there, right? So we're going to mostly focus on the bottom of these 2 here is where our atmospheric chemistry comes from. But anyway, this is kind of the overall layering of the atmosphere. There is, right here, a position. I always mention this because it happened about 8 or 9 years ago. Somebody got into a big suit sponsored by Red Bull and jumped off of a orbiting spaceship and said that was their first manned space jump, right? And there's a whole bunch of stuff about how the guy had to have things in there to wake him back up because he most likely was going to pull so many G's, he was going to pass out, and they were worried he would die in the suit and all that. So, right, that was the Red Bull space jump. It was a big deal. Everyone was so impressed about Red Bull being able to jump from space, but the problem was this is where space starts, right? So they were not even close to where space actually happens. So they just jumped from a really high height and not from space. But anyway, science for science nature anyway. So that's kind of the idea for where space is. Of course, this is where we're going to focus on our chemistry because, like I said, you're not going to find yourself very far up in the atmosphere, most likely trying to breathe or study the interplay between all the gases that are right around there. So this is mostly what our area is. Of course, it's a lot of N2 and O2 and some water vapor and so on. Depending on where you are, the percentages change, but that's the general idea of where the atmosphere sort of is developing. And right here is the star of the show, which is the ozone layer, right? So that's kind of what I wanted to focus on, is the chemistry that's kind of developing the ozone layer and kind of keeping it there. And the story I want to tell you is the story of how we found out that we were doing things here on the surface that were not so good for the ozone layer. So that's kind of the overall gist of this discussion. There is, however, one last thing I wanted to point out, which is this purple pinkish line, which is shown around here with the Kelvin temperature. So that's a very important relationship between the various areas that we're studying. I don't know if you can tell, but where the atmosphere is basically here, and this line kind of meanders around in terms of the relative temperature profile that you see there. And that's an important idea because it lets us know the relative chemistry or the mixing that's available in those particular. Really? Babe. Hey. Sorry, everybody. She's printing.
I just have 2 more to do after this. Can you pause it? Can you pause it?
I don't know where I was.
Oh no, Ryan. Sorry.
One last thing I wanted to point out was this purple pinkish line, which is kind of meandering around in the bottom half or so of the atmosphere, right? So again, we think about the atmosphere as this bottom 80 kilometers, and this pink line shows you the relative temperature profile, obviously in Kelvin, of the gases there. Now, of course, it goes up here and gets bizarrely high in terms of the amount of heat it seems like you've got there. That's the speed of the particles is as if they're at that high of a temperature. Of course, the gas is too thin to really distribute that heat efficiently, so you stick a thermometer out of a weather balloon or a satellite, you're not going to see it read 1500 Kelvin. It'll be very, very, very low because the gases are so sparse. But the gases move with enough speed that kind of makes it seem as if that would be what their root mean square speed is from the temperature they've been given. The point is, this is the more important part of the atmosphere is where all the gases are, and this is the profile for at least the bottom 3 pieces, right? The troposphere, stratosphere, and mesosphere. In fact, let's blow that up so we can actually take a little closer look at those various areas. Again, in case you can't quite get the kilometers yet, because this is your first semester with the metric system, we have basically from 0 to 100, which goes about from 0 to 62 in terms of the miles there. So here's that meandering line, which shows you the relative temperature profile that the bottom half or so of the atmosphere shows. I'd like to point out that anytime it goes through an inversion, right, where you have the slope, I don't know if you guys remember that from algebra class, or the derivative there changes sign essentially. I don't know if you like the word derivative here in the extra credit lecture for chemistry, but there's a switching of the profile being in terms of this, a negative slope to a positive slope, back to a negative slope over there. Anytime we have that switching of the temperature profile, that's where the two, at least for our bottom pieces, that's where they're delineated. So the so-called tropopause is around 15 kilometers on a regular day, or about 9 miles up. That's where, again, in a normal kind of atmosphere, no hurricanes or extremely dry conditions or super, super crazy kind of weather happening, you've got that layer right here, the bottom 15 kilometers, is the troposphere has this, warm air below cold air, versus now the stratosphere, it switches right about 15 kilometers again in a regular kind of day. We see now the temperature start to increase, eventually then goes through another inversion, which is where the stratosphere ends and the so-called mesosphere starts. Again, that's the difference between, at least one of the differences between the bottom 15 kilometers and then the next 35 or so kilometers. You have warm air on the bottom of the layer here versus warm air on the top of the layer over there. A couple other things about this, the pressure drops very quickly once you get a little bit away from the surface, because the particles then, the further up they go, the less often they collide with stuff, and they have a little bit further they can move away. So just kind of naturally from the population of particles near the Earth surface getting less and less sparse, there's less overall particles there, the density goes down, the mean free path goes up, and they can kind of wander off a little more efficiently, but they can't do that unless there's a very low overall particle density, i.e. pressure, So again, most airplanes that you take fly somewhere in here, and the pressure outside the plane is extremely low. So again, they say the cabin is pressurized for your comfort. They probably should say pressurized so that you don't die, is more kind of the comfort that you're going for there. So anyway, there's your relative pressures for the various areas. And again, the most important thing to get from this is the idea that we have warm air below cold air in the troposphere and warm air above cold air in the stratosphere. Why does that matter? Well, it leads to a lot of possibilities for mixing in the bottom layer and not so much mixing in the top layer. Here's a French diagram that shows the relative, let's say, jet streams and sort of effects you can see with weather. So again, just to give you a little orientation, here's 0 to 50 in terms of the kilometers up, so kilometers over here. Here's the equator, so of course that's 0 degrees, and then we go kind of north up to here to the pole nord, which is this area on the top. The point is, with warm air near the surface, why is it warm? Because the Earth has a lot of heating it goes through during the day, and it radiates heat while it's the sun's down. So we have the relative warming of the surface warming up the air right above it. That air, if it's warmer, what would the ideal gas expression say? It's going to have a larger volume, right? The larger the volume gets, the lower the density goes. And if something which has a low density is on the bottom of something, it's going to rise up, right? So the idea is they have the density of the air being inverted, right, in terms of low density and high density above it. That's going to cause them to mix. So at the bottom, at the Earth's surface, there's this push essentially of air up. Now it mostly starts from where the Earth is the hottest, which is around the equator, right? That's where most of the sun is hitting. So we end up having a lot of air being pushed up there. And as you can see, we get these different little cells that evolve because of the mixing of the air, right? When warm air and cold air mix together, there's usually this compression of the warm air or this expansion of the cold air. They have to kind of come to a happy medium. And when they do that, there's a possibility for collecting of water droplets, i.e. making rain. So there's a lot of weather that happens because of the troposphere having this bottom layer, which is warmer than its top layer. However, we get to eventually around 20 or 30 or 40 or so kilometers, and now we have relatively still air because now the top of it's the warmest portion and the bottom of it is the coolest portion. You can maybe make out the dotted line here shows you the relative temperature profile that's following along up the atmosphere. The point essentially is now the air goes whoosh flying up here and eventually makes its way back down, which is called subsidence, basically a fancy word for air falls back. So we have this constant amount of air kind of circulating around, which gives us relatively predictive weather patterns, which we've evolved to know, hey, we should live in this part of the Earth and not in other parts of the Earth, right? Where it's really, really nice climate, weather is enough for rain and we can grow food and all that kind of stuff, where it's not cold all the time like the North Pole or way too hot to live and no water around on the Earth's surface like it is at the equator, right? So we've again figured out where the good places are to live based upon how the troposphere mixes all of the air at the bottom of it. The other complication though, of course, is if we have gases which are emitted anywhere down here on the right surface, they are purposely then by the Earth going to be mixed around everywhere, which is again I don't want to get too political and all that kind of stuff here, but that makes pollution a global problem. Just because a gas is made in China doesn't mean it's not going to make its way here, or if a gas is made in the San Fernando Valley, it's not going to make its way all the way over to Crete in Greece, right? So whenever things are emitted on the Earth's surface and they have a long enough lifetime, they're not reactive enough, they can eventually make their way all the way through the entire atmosphere. So that's why the idea of pollution is everybody's problem and not just the people that live in that city. So that's kind of the idea behind the troposphere having this high temperature on the bottom and low temperature on the top. Now, if you're wondering, why does it do this? Why does it go up again in the stratosphere? I'm not saying that yet because that's part of our discussion a little later. But anyway, that's the idea for at least why is the tropospheric, they call it the inversion layer, right? The inverted amount of density on the bottom and top being not natural. That's one complication that the troposphere shows that the stratosphere doesn't show. Another thing which is different about the troposphere and the stratosphere is the amount of radiation that makes it into the troposphere versus the amount of radiation which is present in the stratosphere. Now, when I talk about radiation, I'm talking about electromagnetic radiation, right? Light, essentially. So to show you the difference between what is hitting the stratosphere and what is actually hitting the Earth's surface, I have two different plots for you. Here's a picture you might be taking, again, kind of a figurative picture. You take a picture of the sun when you stand basically above the atmosphere. Now, like we said, the atmosphere traditionally is thought of as mostly about 50 kilometers and down, or maybe 80 kilometers and down, right? So the stratosphere and the troposphere, the two major areas where the air is thick enough for us to essentially make some comments about the chemistry that's happening there. So here's one thing that you can do. Take a picture, again, figuratively, if you stand on the top of the stratosphere and take a picture of the sun and plot up all the different wavelengths you see, this is what you're going to see there, right? So the wavelengths that you get coming to the Earth's surface are pretty intense, right? Again, this is the intensity over here on the left side. We have pretty intense light from, let's call it about 300 nanometers all the way out to about 1250 nanometers. Now you might remember from about 400 to about 700, that's visible, right? So a huge amount of the light that gets to us from the sun is visible light. An awful lot of it also is then not red, but then this part over here is infrared, which you might know as heat, right? So a very large amount of the sun's energy that gets to us is in the form of either visible light or heat. A small amount of it, though, is also in not violet, but for some reason it's not infraviolet, but it's ultraviolet, right? So there's ultraviolet for the most part over here, visible, and then heat. Those are the three different kinds of wavelength spectra or wavelength portions that hit us from the sun. Again, hit us meaning hit the outermost areas of the stratosphere. This red line is now the exact same photo, but you're going to stand at the beach and take a picture up through the atmosphere. So again, the difference between the blue one and the red one is the red one allows the sunlight to pass through the troposphere, right? It's passing all the way through the entire atmosphere. So of course you can see there's a whole bunch of stuff that happens. Obviously the entire curve is muted. Muted meaning there's less overall intensity, right? So we still get a whole bunch of visible light and we get a bunch of infrared coming through. There are also, though, some major differences. I want to point out what I refer to as the pits that are here. There are some pits, let's say, for example, right here, right here, and right here, and right here, obviously a couple over here as well, where there's not that particular wavelength coming through. Those areas there are what are called the greenhouse effect. The greenhouse effect is what keeps a lot of the heat that makes it into the Earth's surface, keeps it there, right? There are certain areas along the wavelength spectrum, all of which just so happen to be in the infrared portion, right? So again, this area here, this area, and so on, those are heat wavelengths. Those heat wavelengths are not allowed to pass through, which means they're not allowed to pass out. So there's a couple wavelength portions that are blocked from coming in, but those would also be blocked from coming out. Those are then heat that gets radiated back. In case you don't know what the greenhouse effect is, a greenhouse has light that passes through the windows. The windows, though, are specially designed to block heat from coming out. So you don't need very much visible light and heat to pass in for the greenhouse to stay nice and warm. That's what the Earth has going for it. The atmosphere is basically filled with a bunch of chemicals that have certain areas that they're very good at absorbing or reflecting back heat. There are certain areas we have figured out are due to certain gases. For example, this one here, right about 750, it's due to oxygen. Now this is a little bit beyond your pay grade in Chem 1A, but it won't be when you hit Chem 1B/OChem. Molecules vibrate, right? Again, you are aware of that via those Leonard-Jones potentials showing the potential of the two atoms getting lower as they approach each other, and they have this natural frequency of vibrating back and forth based upon being too close. Nuclei say back up a little bit, and then the electrons saying wait, come back a little bit closer, so they kind of vibrate back and forth. Molecules, when they vibrate back and forth, create a little bit of a dipole doing that because of the motion of their positive and negative charges, and it turns out infrared light happens to match that. Not much different than how, visible light can match transitions of electrons in certain kinds of atoms. I'm looking at you, hydrogen, for example. So when infrared light, goes next to these kinds of molecules, it can either absorb or be emitted by the vibrational modes of those molecules. So O2 has a vibrational mode which exactly matches the wavelength of somewhere a little bit less than 750. So that wavelength doesn't come in, but also if it comes from below the Earth, off the Earth's surface, doesn't get to leave. So O2 is an effective trapper, essentially, of that particular kind of wavelength, which we happen to feel as heat. There's a bunch of them over here which are also due to water vapor. Water vapor has 4 different modes based upon the way the 3 atoms there are vibrating back and forth. Now here I always make a joke where I kind of show you the various methods they can vibrate back and forth, and imagine I'm flossing, because that's one of the ones I always try poorly to do. So that's the fifth vibrational mode, is the flossing mode, which of course you can't get the visual for. Unfortunately, that's, I guess, not your loss. Anyway, those are 4 different places where the water is extremely effective at trapping, right, the heat that's trying to come out and keeps the earth nice and warm. There are 2 last little ones right here, little tiny mini guys right there at the end, and those are due to CO2. Now, I don't want to make this the focus of the lecture, and again, I'm trying my best not to get too political overall, but this is one of the things that gets climate scientists, and probably you as well as a younger person, all jazzed up about the effect of basically human populations on how the climate has gone. The reason why we're so concerned, not necessarily about O2 and water vapor, because we can't really get rid of those, but in particular CO2. Another one you might have in mind is methane. It's not on here because it's the vibrational mode is a little too small, but again, methane and other gases. N2O is another one, which is going to be a greenhouse gas. This is one of the ones that contributes to this effect. Those kinds of gases have been skyrocketing recently, again, recently on Earth. The term of Earth is over the last 400 years or so. Those kinds of gases are, we think, having a dramatic effect on the climate. Not necessarily the temperature, but what kind of weather patterns we're seeing. The thing that got climate scientists all up in arms, and continues to, because of the effectiveness of the models that were kind of put together because of this data set, is a data set called the European Project for Ice Coring in the Atlantic at a spot called Dome C. So this is what's referred to as ice core data. So if you've ever heard a climate scientist talking about ice core data, this is one of the original, the OG of ice core data sets. It's called EPIC A Dome C. Again, EPIC A stands for the European Project for Ice Coring at the Atlantic, and then Dome C is a particular spot. They had a Dome A and B and C was the one that gave them the best overall results in terms of the best ice cores, and then being able to make some sense out of it. So what they do in these kinds of experiments, again, what they'd be doing during this EPIC A Dome C dataset is taking this drill and drilling down into the Antarctic ice sheet. You drill down and drill down and drill down, and the point essentially is, it turns out you're drilling down through the past. The reason that happens is because it's pretty much always cold and always snowing at the South Pole, right? Under Antarctic conditions, it's always snowing and always very, very cold there. And because of that, when it snows more than it does because, it was colder, or maybe if it melts a little bit, the point essentially is there's always an amount of snow which is newly falling on the snow below it. And as that happens over the course of hundreds of thousands of years, there's a layer of snow that builds up, and as the snow above it builds higher and higher, what happens? The density of this has to collect to be a little bit lower, right? In terms of under these kind of conditions, it's going to freeze. And they're going to have then this overall freezing of the snowpack that falls down. When it freezes, the theory is it traps some air of that time in little tiny bubbles in the ice sheet. So as you drill down through thousands and hundreds of thousands of years of various kinds of ice, all of which will have trapped along with that ice gas that was basically a tiny, tiny little sample of the environment at that time. So you can then drill through, get a picture of what was happening hundreds of thousands of years ago based upon the composition of the gases that are trapped along with the ice. So taking an overall look at this, you can see there are 4 different lines on there. There's a green one, a black one, a blue one, and another kind of black one on the bottom. Let's first point out the bottom one there. If you can see that it says little partial D, and then it says 0 per 1 per 0, 0. So this is what's called parts per mil. It's a way you can measure the amount of isotopes that are present. So the bottom of this shows you the relative amount of what's called heavy water, which is in ice. Now the amount of heavy water there, scientists and geologists have used as a proxy for temperature. Let me explain to you why. So what the temperature scale uses is essentially the difference between the freezing points of various forms of water. Now I know that sounds weird because we think of water as having one kind of freezing point, but out in nature, as we're talking about, there's various different isotopes of either H or O that are naturally forming and therefore naturally make their way into water. So the regular water, we kind of talk about when you drink water for the most part, is mostly
H2O, where the H and the O's are the most likely isotopes of those, H1 and O16 as the two different isotopes there. That sets up a certain mass for the water based upon the nuclei that are present, versus now naturally forming deuterium and then oxygen 18, they can find themselves in various manners, right, peppering into the water molecule, and you could eventually get them what I'm kind of calling heavy water here. Heavy water has obviously a larger overall mass, but it still is considered water because it has those nuclei in it. The point is, this molecule up here is going to be lighter than that molecule. So by KMT, which of the two of them would naturally move around in space at the faster overall speed? This one, right? So if we give these both the same energy, this one's faster. If particles are faster, that makes them harder to slow down. So this kind of species here actually is easier to freeze as water, not because it has a different kind of strength of attraction, but because it's simply a slower molecule. So you don't need to get as cold to see elevated amounts of this. So if the ice has elevated amounts of heavy water in it, as we saw in the little plot, that indicates a warming overall for the temperature. And if there's essentially, right, not elevated amounts of this, regular amounts of this present, then it was either, right, regular temperatures or colder. So this is a proxy for temperature because more of this there just means this was freezing at a, right, higher temperature than this one was. So whenever this gets elevated, that tends to relate to global temperatures being higher.
So basically this bottom line there, right, the bottom EKG we have on the very bottom of this curve, the spiking you see there is where there's more of the heavy water present. The point essentially is the times that that's occurring, it meant that there was a higher temperature than normal. Again, the normal meaning when all the different kinds of water are kind of evenly about to freeze. What I want you to notice then is every time this thing has spiked, other gases along with those, again, those little tiny bubbles that are trapped along with the gases, they're spiking also. Every single time this occurs, the blue curve seems to follow along with it, spike, 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 all the way through there. The other black curve, boink, 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 spikes very almost similarly to those. And we have a kind of incomplete data set for this green one, right? That's the N2O. We do, though, see a little bit of spiking with that one. The one that's, of course, gotten climate scientists so concerned is the black line through the middle here, which, as you can see, is the carbon dioxide, so-called ppm. ppm stands for parts per million. So what that represents is if I grabbed 1,000,000 parts of gas, how many of them would be of a certain kind? So if it's 1 ppm, 1 CO2 particle would be there for every 1,000,000 particles of gas. Again, not merely N2 and O2, but just the entire collection you have. The point, again, that you're supposed to notice here is CO2 is following pretty much exactly with the temperature spikes. So one of the things that scientists have been putting together is the relative level of CO2 either is a residue of or a cause of this change in the global temperature. Global temperatures go up, CO2 tends to either be the cause of that or at least be related to that. Again, there's a whole almost 1,000,000 years of data here, which pretty much shows almost with a correlation of very, very close to 1, relationships between when the temperature goes up, the CO2 concentration goes up. Now, this data set was collected a little bit before 2008 and posted, and in 2008, they were saying, look, if we put onto it this iced core data set, the current levels of CO2 that we have, this would be where we are right now. So again, in 2008, they were like, look, this is us at this point, higher than any of the last almost 1,000,000 years of CO2 data has ever reached. So again, in 2008, we were in unprecedented territory in terms of the amount of CO2 which was there, which of course means let's figure out what the F is going to happen to this, the temperature that's present. Well, my cursor got big there. So the point is, right, in 2008, they were like, yo, it's getting really high. This was, what that say, about 360. I don't mean to make you get too scared, but you can go to a website called co2.earth, and it tells you from some various observations out in Hawaii and different remote places what the average ppm of CO2 is for every month since they've been starting taking them. So here is the latest data set for how much CO2 on average this thing collected in April of 2020. 417. Almost 100 more than the model had where it was like, ugh, we don't know what to do, right? And you can see, of course, all the other ones. Methane is spiking out of control recent times as well. So again, methane is an extremely important gas that goes along with this. CO2 is though more along the lines of right the burning of fossil fuels. Obviously CH4 is maybe kind of how we're eating with cows and that kind of stuff. So we have two gases which are normally not at these kinds of levels that are, we believe, either in the middle of or about to dramatically affect the climate. So that's where maybe you're interesting. You are obviously very interesting, but maybe that's where you're interested in where this goes next, right? That's what got me into or get into atmospheric chemistry, was just this kind of bleeding heart environmentalist in me that wanted to save something. I wanted to be part of right the solution that goes along with it. So this again is the motivation for why we want to study the atmosphere, especially with our ability to have nice places to live, fresh water, nice food, and all that kind of stuff. And again, I will ignore the politics that are going along with this because I want to focus on our story, which involved a success battling through the politics of the time. But this is the data set where people are like, yo, climate change is, or climate scientists and climate change is a very, very real thing, and we need to be concerned with it. And we are finally kind of, I believe, over the hump in terms of getting people to understand the at least reality of this. Again, whether or not we can do anything about it, that's a whole different bag of beans, to make up a new kind of metaphor. But point essentially is it's beginning to now be taken seriously. But anyway, the more importantly for us, right? Again, all the different pits that are there, the various areas where right we have this greenhouse effect occurring. I want to focus though for this lecture on the difference over here. So again, the difference between this troposphere and the stratosphere seems to be various amounts of energies that are either coming through or not coming through. Again, the blue line, just to refresh, was how much energy the sun shoots at us. The red line is how much energy actually hits the surface. There's a little bit of a gap between the types of energy, let's say in the UV, that are coming toward us and that are not making it through the stratosphere. So this little green box here represents the difference in these sorts of ultraviolet wavelengths that are not getting to us overall. So, there's something happening in the stratosphere which is, of course, preventing those kinds of wavelengths from getting to us. I bet that's an important thing that allows us to develop the kind of life and society and environment that we have down here as well. Okay, so what are some major differences between the troposphere and stratosphere? That sounds like a good question. So come out of your coma for a second. This would be one of the questions you'll be asked on the exam. Final exam would be one of your extra credit questions. It'll be as easy as, what are some differences between the troposphere and stratosphere? It's going to ask you to, according to the extra credit lecture, what are the major differences? These are the three I would like you to quote back to me. So first off, of course, is the height. Stratosphere is around 15 kilometers. That's where it starts. The troposphere is the below 15 kilometer area. The profile of temperature, and again, we talked about why that matters. There's mixing, there's weather, and there's the ability of us to all worry about pollution as a globe versus as city to city. So that's the other difference, right? Troposphere, warm air below. Stratosphere, colder air below. And then lastly was the energy that actually makes it through each. The troposphere ultraviolet photons tend not to survive the trip through the stratosphere for some, as for right now at least, unknown reason, versus the stratosphere has a wider variety of those photons available. So that's the basic idea. Again, you can do height, you can do temperature profile, and you can do radiant energy. Those are the three differences between the troposphere and the stratosphere. That's going to be the question that'll be on the exam for one of the extra credit points. Okay, so of course, the focus then has to be, for at least this lecture, on the difference then and how do we get these photons that are of lower wavelength / higher energy, how do we get them to be absorbed somehow? Now, we talked in this class, a little bit at least, about ways that molecules can absorb things. You might remember this from right before spring break, right? In fact, this is one of our last things but one of the last labs we were able to do with the computer was, right, the Beer-Lambert law. So photoabsorption is one way that light is blocked or absorbed somehow by a molecule. So again, we have the two different cones of light coming in. So that's the light that the little ocean optics box was shooting at your cuvette here. That's the light that comes through. It detects the difference there between it. The point essentially was, right, the more absorption you have is either because there's a very strong ability of a particle to absorb, there's a long path length that goes through, or there was a high concentration of whatever the molecule was that we were absorbing. The point here is the molecule, when you push this light through it, you just excite the molecule. There's some electron transition in some bond someplace that essentially absorbs that overall energy, right? And we have the different pieces that we can measure about that. The point I'd like to make is that doesn't change the molecule. Here is the absorption of ozone, for example. Again, I'll pick, not randomly, but not, you'll see why, kind of seemingly randomly, I'll pick ozone off of here. Again, ozone was the ozone layer we were kind of talking about earlier. If you fill up your cuvette in the lab with ozone, obviously put a little top on the top of the cuvette, and shove your light through it, you'll see it does a pretty good job of absorbing around 500 to about 700, so it's got a little shoulder here, but the point essentially is it's good at absorbing the light within the visible portion of the spectrum, right? Again, it's pretty good at that. Now, that doesn't help us understand, though, why was there this blocking of ultraviolet light? Remember, that's the thing I want to focus on, because there's plenty of this visible light that gets to us. Obviously, it's daylight, maybe right now when you're watching this, so obviously ozone is not blocking all of that visible light, because the sun comes up and it goes down because of the motion of the earth, not because of gases, right, absorbing that energy. The point essentially was, though, ozone doesn't get broken apart. It stays as an ozone molecule. It just absorbs this light because the bonds somehow have some energy of the electrons changing a little bit upon having this kind of energy pass through them. The other thing, which I never thought of when I was in undergrad, when I was your age, I was doing chemistry classes and trying to survive and monitor or navigate my complex relationships and all the same stuff, but I never thought about the atmosphere as being this gigantic photoreactor. Photoreactor, of course, means you have reactions that occur because of photons passing through. It turns out, because of the high energy of photons, especially the ones we're dealing with here, which are ultraviolet, they have enough energy to actually cleave bonds within a molecule. That's called photolysis or photodissociation. Again, first day of atmospheric chemistry completely blew my mind when the professor was starting to talk about photolysis rates, and the idea that sunlight could possibly break molecules apart never occurred to me at all. That was a possibility, but it is. It's a very, very huge part of the chemistry of the atmosphere, is that half of the day the gases are bathed in light, which might be energetic enough to just react with them by breaking them apart into other things. For example, NO2 here, right, nitrogen dioxide gas, could be broken into NO and something called O-triplet-P simply by being hit with a photon, which is less than 420 nanometers, right? A high enough energy can actually break the bonds within the NO2 molecule and form two new things. Guess what else can do this, right? In addition to being good at absorbing and staying intact as ozone molecules, an ozone molecule can actually react with light below 330 nanometers and produce what are called two dissociating channels. Channels meaning literally like you can tune them to a TV show. So if you want to tune it to a channel where it makes something called O singlet D, you can kind of play around with the wavelength you're using. Or if you want to tune it to a channel where it makes O something called triplet P, you can then tune it basically based upon the wavelength you're using. Again, this is a monstrous concept in terms of atmospheric chemistry, understanding the kinds and the various products you get when molecules literally react with photons. Again, the photons are kind of the one doing the reaction because they happen to slam into the molecule as they come through the atmosphere. But this again is the idea of photolysis. Now, real quick, what's the difference between O singlet D and O triplet P? Well, meet me at the whiteboard for a second.
So here's the difference between the O singlet D and the O triplet P, right? The ground state version of the O atom and the excited state version of the O atom, at least one of the excited states. I have the electric configuration for both of them drawn here. If I gave you 10 seconds, you're probably going to be like, well, wait a minute, something looks like there's something wrong on the bottom of that one, right? Because here we've got these two electrons that are violating the Pauli exclusion principle, right? They're both in the same orbital with the same spin, which supposedly is illegal. Obviously, that's illegal if you're going for a ground state. This is one of the possibilities for how an O atom might be created with an excited state along with it. So that's the difference between O triplet P and O singlet D, right? O singlet D has that set of electrons which is excited. It makes it a little more reactive than this one, because this one's looking to get rid of some of that energy, right? Be able to deactivate and relax down to the O triplet P right there version. So there you go, some spectroscopy for you today.
Along with the idea of, right, being able to be split apart into various products, right, either the excited or not excited version of, let's say for ozone, the oxygen atom, we also measure the yield of these, right? So you guys have been talking about percent yield. If you do a photolysis reaction, it kind of sounds really funky, right? It has a funky symbol, phi, right there, but the reaction's percent yield when it relates to, right, photons reacting with intact molecules to break them apart, the yield of that is called the quantum yield. It has a kind of complicated sounding definition. It says here, right, number of molecular dissociations divided by total number of photons absorbed. But basically the idea is the higher this goes, the more efficient the reaction was. Let me give you an example. Let's say we've got 10 molecules of ozone lined up over there, and I shoot 10 photons at it. The quantum yield says, well, how many of those photons you shoot at those 10 ozone molecules produce a dissociation. So if we say the quantum yield was 0, of course that means that none of those particles were dissociated by the photons I shot at them. If we say the quantum yield is 0.8, that means 8 of the 10 particles were dissociated. So not only do you concern yourself with, is there a possibility for a bond to be broken because of light passing through? It's not just, is it enough energy? You actually have to, right, have a high enough yield for this. So you're concerned usually for these kind of photolysis reactions with two ideas. One, is there even going to be a reaction in the first place? Is the energy proper to break it apart? But secondly, what's the quantum yield, right? Just like any reaction, you want to say, is it a good reaction? Am I worried about it? Is it efficient? If the quantum yield for a reaction is very, very low, it's not going to be a significant reaction in the atmosphere. If the quantum yield for the reaction is high, approaches 0.8, 0.9, or approaches obviously 1, then that means that reaction definitely happens and you need to be concerned about the result of that reaction. Or that could be explaining maybe what you observe if you have a very high quantum yield for some kind of photolysis reaction. I'm not sure if you know where this is going, but that's of course one of the focuses was this idea of what the ozone's chemistry is. Why do we give a crap about ozone in the first place? Well, here is a plot of, it's a very fancy sounding plot here, so get ready to be very, very scientific when you read through with this on me. Over here we have the quantum yield, right? That's the plot of the quantum yield, which you know represents the efficiency of that particular reaction. And of course, here's the wavelength. Now it goes from low wavelength to high wavelength, so high energy over here and low energy over here. It's a scary looking plot of all these crazy little data points. Not that it matters to you, but the little bars around each side are what are called error bars, which are these fancy things that are basically for a plot the plus minuses. The point I want you to see is a whole bunch of groups have studied the reaction of light with ozone, and they're studying the particular channel which produces O singlet D. Again, who cares about that? The point essentially is ozone here is being shown to react with light. What are you supposed to get from this? Well, hopefully you're understanding that if we have these relatively high wavelength / low energy photons we shoot at it, not much happens, right? This reaction, O3 plus H nu or HV giving us reaction essentially doesn't work for these low energy photons. Quantum yield is very, very low. But we start approaching a threshold of, let's call it about 305, maybe 300 or so, around 310, we start seeing pretty much a quantum yield of 1. Again, what does that mean? It means every single time a photon interacts with ozone, there will be a reaction. So ozone has this extremely very, very strong taste for, or has a very efficient reaction with light that hits it when the light is below around 310 or so wavelengths. In fact, this is the reason we think why there's that gap between the kinds of photons energies that the sun shoots at us and that actually makes it to us. The ozone molecule is the one responsible for essentially diving in front of all those high energy UV wavelengths and reacting with them to absorb them. So ozone is the responsible party for why we see a lower overall amount of high energy photons coming through the stratosphere. The stratosphere, as you might already know, and if you don't, you're going to learn about it now, is chock full of ozone. Those ozone molecules are about what was it, about 50 or so kilometers above us, 30 or so kilometers probably on average, right? Absorbing all of these high energy ultraviolet photons. So this is a very important plot for us understanding the importance of the ozone molecule. So with that said, obviously the ozone is this thing that's protecting us from these ultraviolet light rays coming in. I am sort of thinking about what questions you might have about the ozone layer if you don't have it. First off, you might say, well, where is it? This is a plot of the relative, what are called ozone pleths. It's a very fancy word for essentially the contour plot of ozone. You ever seen a contour map where it has all these crazy lines and numbers all over the place, and you're supposed to look at that, and if you know what you're doing, you go, oh, let's go here, because that's going to be a nice elevation change. Whenever I was like hiking with somebody, I'd be like, why'd you point there? That looks like nothing. I don't get it, right? So this is essentially showing us the relative height, let's say, of the stratosphere, but also the relative concentration. So, for example, the purple ones, that represents a very low amount of ozone, but as you start crossing these lines, there's a 2, there's a 6, and there's so on. That shows you the relative partial pressure. Oh, there's a word you know. The partial pressure of the ozone there. So, of course, these really, really high numbers, right, 18, 20, and so on, that represents a very large amount of ozone. So the ozone layer tends to be spread on a normal, healthy kind of day between about 16 and 40 kilometers. So it's all up there, very large amount of ozone, for the most part, distributed all the way across the Earth, right? So a big belt around us, essentially, showing us where all this ozone essentially sits. So that's where the ozone layer is. You might ask, well, what's it even doing there? How come we have ozone in the first place? That's a good question. Who put it there? Was it the aliens when they left? They farted and a bunch of ozone came out and they left it as they were leaving? No, that's probably, hopefully, that's probably not what it was. It probably was some relationship between the building up of oxygen containing atoms or molecules and eventually kind of collecting in the atmosphere and reacting together and sort of chain reacting, continuing that particular kind of reaction. So the mechanism we believe is responsible for building ozone in the first place is something called the Chapman mechanism. It's very, very simple. As oxygen built up because of photosynthesis and the ability of particles to produce more oxygen here on Earth, oxygen built up and eventually would find its way to places where there was 242 or less nanometer of light, which, let's say, in the early atmosphere would have been pretty much everywhere. Turns out that energy of light is able to split O2 apart into 2 O singlet D particles. Again, remember, O singlet D is the excited version of the oxygen. Turns out the excited version of oxygen pretty much will react with anything it sees. One of the very common reactions it does is what's called a collisional deactivation reaction, which is exactly what it sounds like. It bumps into something and deactivates, becomes a regular flavored, boring type of O atom, which has its regular electron configuration, which you may remember from 5 or 10 minutes ago as O triplet P. O triplet P, as it turns out, is something that could then live long enough, most likely, to react with another O2 molecule and other things. Again, we're focusing right now on the kinds of reactions which eventually produce ozone molecules. The O triplet P lives long enough to do an efficient reaction with O2 to produce ozone. And this continues to happen as the O2 particles are being developed, they build up, and it turns out this reaction starts kind of making a bunch of O3 particles. This is kind of what I didn't want to spoil earlier, but remember I mentioned I'm going to talk later about what the warming trend in the stratosphere is. We believe this is the reaction, the middle one here, the collisional deactivation. We believe that's the reaction responsible for the stratosphere being warmer on top than it is at bottom, The minute this kind of ozone dissociation occurs, all the O atoms that are produced upon that could possibly react and make ozone back, And if they do that, they're going to collisionally deactivate first if they happen to be made as an O singlet D. So the O singlet D that's produced by ozone photolysis eventually produces some energy because of the deactivation it has to go through before it can eventually react with something else. So it's kind of like a snake eating its own tail. They kind of self-generate themselves as they're going through these reactions. So that's why the stratosphere warms back up. Ozone is responsible for that, essentially. So there's where ozone comes from in the first place. Who cares? Why is ozone there at all? Or why do we give a crap about that? Again, we are all very narcissistic in terms of what's this do for me or for us, let's say, as a human race. Well, I've been hinting at this, but it protects us from very damaging UV light, You, of course, me and all of our family tree essentially has been able to live in an atmosphere which has not had this extremely large amount of ultraviolet light passing through it. That, of course, is good for us. One, well, look up here. O2 seems to like itself some ultraviolet light. So theoretically, if there was no ozone layer, then O2 anywhere could be broken apart into O atoms. And you probably know this already, but you don't want that to occur. You don't want to have no oxygen in the air. You don't survive on O atoms, you survive on O2. In fact, your extremely complex chemistry of respiration and getting energy is extremely tied to a very particular pressure of O2 being brought into your lungs once or twice every minute. And if that gets disrupted, guess what? You're gone, right? So this is an extremely important idea that the O2 molecules we have down here in the troposphere, we don't screw around with those. Ozone helps protect the relative concentration of tropospheric oxygen. It's also, of course, not very easy to grow stuff or have things live for a long time when they're underneath this bombardment of extremely high energy photons, right? So again, plants and plankton and things that other stuff eats, that other stuff eats, that other stuff eats, really wouldn't get going very easily, right? So if you're like, well, I don't eat cows, so I don't care about plants, well, you probably do eat plants if you don't eat cows, right? If you're like, I only eat fish all day, well, fish eat plankton and the fish would not have anything to eat if all the plankton died, right? So again, if all of a sudden we just Thanos'd so snapped our fingers and all of a sudden all the ozone went away, it'd be a pretty rough 4 or 5 days before we figured out what the hell to do. You'll be able to go outside, but we're not really going outside much anyway anymore. So who knows? Maybe the ozone layer is really healthy at this point. I have some notes about that later. Okay, and lastly, again, if it's like, okay, great, whatever, I don't care about the O2, I don't care about plants, I care about me. Well, if you had a bunch of UV light outside when you went outside, you would get skin cancer pretty fast. You'd get a bunch of different kinds of eye diseases. Life would be a lot different because you'd probably have to walk around with an umbrella all the time, even when it's not raining. Or I used to make this joke, right? We used to say, well, if you get glaucoma, you can get a weed card, but you don't need a weed card anymore. So I guess that's out the door. So don't get glaucoma just so you can get weed. You can get it legal now. It's fine. Anyway, those are the 3 and of many other reasons why we have ozone, or why we care about the ozone layer being there at all. Okay, the other thing you probably, or at least I think you might be sort of moderately to somewhat interested by is, why is there a layer, right? How come the ozone layer seems to be only in that little tiny bit of the stratosphere? How come it's not the entire stratosphere, or why isn't the entire atmosphere ozone, right? Looks as if it kind of grows itself back. Why didn't it grow to be the entire atmosphere? And then why does it hang out in that one little area? That's a very good question, and the theory is the ozone layer itself is controlled by, I'm only showing you 4, but 4 basic depletion cycles. So I kind of refer to these 4 particles here as having ozone hunters inside them. There are 4 different cycles which are regenerating a particle which can react with ozone. This, of course, is not a big deal for you, the idea of ozone depletion, but I grew up in the very tail end of the hysteria behind ozone depletion, and ozone depletion was a very, very, very big concept. I'm going to explain to you how we figured out and solved the issue. So you have lived underneath of the idea that ozone depletion is not a very big deal, but ozone depletion, I've said it enough, it turns out to be the reason why the ozone layer hasn't grown to be the entire atmosphere. That wouldn't be any good, right? Ozone itself is actually kind of hard to breathe. You get asthma and you get irritated by breathing ozone. So ozone above us is very good. Ozone in our backyard, not so great. So ozone didn't grow to be the entire atmosphere because of these regenerating ozone depleting reactions. There's the Knox, Hox, Brox, and Clox cycles, these Dr. Seuss named reaction cycles, where essentially through them, they're kicked off by some kind of reaction which eventually goes after ozone. So again, just to get you orientated, here's the Knox cycle. NO reacts with O3. Again, why is that? NO is a radical. Remember, radicals have unpaired electrons in them, and they are more on the hunt for a particle to react with than normal. Notice how all 4 of these are started by the reaction of some kind of radical species, right? Those are more reactive than not. That's a very big deal in atmospheric chemistry, thinking about the radicals that are around reacting with things differently than molecules that are having all of their electrons paired up. The point essentially here is the reaction will produce the same original particle back. So NO could react with ozone and eventually be produced again and restart the cycle. Same with this one. OH radicals can be reacting with ozone and eventually reproduce themselves and restart the cycle. Br and Cl, same thing. So these are all 4 naturally occurring reaction cycles that are basically keeping the ozone level layer in check. So that's why I call them hunters, because they're there to essentially this is not what they're born to do, but they are there to help control the population of ozone. I myself am not a hunter, but I grew up in Michigan, and there was always hunting season. It always seemed like there was a different kind of hunting season, because there was gun season, then there was bow and arrow season, then there was build a trap, jump out of the ground and rustle them to the ground and choke them out season. I don't know. There's all kinds of ways to hunt deer, various ways, but the kind of weapon you could use seemed to change every so often. The point is, we do that in Michigan because if you don't do that, obviously people don't have any fun, but also, right, the deer population gets out of control. If you hit a deer in your car in Michigan, you have to call the police. You have to basically write a report about it, not like to your teacher, but like the police have to write it up. It's a big deal because, right, the amount of deer that are around, if they're getting higher or they're getting too low, it's kind of like this layer, right? So we have to have this nice happy amount of deer so that we can see them and pet them and all that kind of stuff. But also we don't want too many of them because they'll ruin all the crops. They'll overrun the forests. And you have to essentially, right, control the population. So NO, OH, Br, and Cl are among the 4 best ozone hunters. In fact, chlorine, of the 4 of them, is the best. It's the #1 killer of ozone, let's say. It has the most. It's like Rambo out there, right? Or whoever you think is cool as a mercenary. I don't know if Rambo's still cool anymore. Probably not, because Rambo came to mind for me. Anyway, Cl is very, very good at this. By very, very good at this, I mean has a very particular taste to react with ozone. Of the 4 of them, Cl is the best. In fact, scientists estimate that one Cl radical will go through about 100,000 ozone molecules before doing some other kind of reaction. It's almost as if Cl knocks other particles out of the way and targets ozone in the stratosphere. So Cl is a very, very good ozone hunter, and that now will be the focus for a little bit. Where does Cl come from? And you might be able to see this. If the amount of Cl we put into the stratosphere gets out of balance, now we have all these Rambos up there looking to, right, take revenge on whatever it is that the ozone molecules pissed them off about, and they're going to Ramboize all the ozone they can find, right? So, of course, the one that we're most concerned about in terms of the health of the ozone layer of these 4 is chlorine. So you might ask, well, how does chlorine even get there as that particular kind of molecule, right? The Cl radical, where's it even getting there from? There are actually 2 different sources that are, on average, monstrous sources of chlorine into the stratosphere. One is what are called methyl halides. Methyl halides are obviously methyl, which is CH3, and then halides, which is one of the halogens. Methyl chloride, which is this one here, the CHCl3, that comes from plants, right? It turns out rice paddies and certain kinds of vegetation emit an insane amount of these methyl halides, one of which, of course, is CH3. It also turns out a lot of chlorine kinds of compounds come from what's called biomass burning, which is like wildfires and things like that, which there have been quite a few of, obviously, lately. And, of course, volcanic eruptions, which don't happen too often, but when they do, you've seen the pictures of Vesuvius or anything that's happened with the Hawaii thing a couple years ago, right? It's just like towering, monstrous amounts of gases. One of the major components of those kinds of gases is of course, sulfurs and all that kind of stuff, but also we get quite a lot of chlorine compounds. So these 2 here have given us this natural baseline of chlorine, which eventually some of it finds its way into the stratosphere. That gives us this low enough amount of Rambo chlorine atoms up there to control the ozone layer, but not so many that they kill them all, essentially, right? So the Earth has come to this natural balance between natural sources of chlorine here and natural residues, let's say complications or natural consequences of the Cl, which eventually gets out into the atmosphere. One of those is helping to control the ozone layer. However, in 1930-ish, DuPont and Merck and other chemical companies invented something called chlorofluorocarbons, which are CFCs. Chlorofluorocarbons were invented because of their chemical inertness, and they were very, very helpful in doing two major kind of industrial processes. Styrofoam was invented in 1930 or so, and it had to be blown into various shapes. Now, y'all are way too young to understand this, but when you used to go to McDonald's in the 80s or early 70s, which is kind of when I came online for McDonald's. It wasn't just McDonald's, but McDonald's, of course, was the most ubiquitous fast food restaurant. But all the restaurants would do this. They'd give you your burger in a big styrofoam container. So, for example, here's what the Big Mac used to come in. And I can remember as a kid, when I would throw my stuff away, my parents would yell at me not to break it apart, because when they make the styrofoam molds, right? The styrofoam comes as kind of a liquid and has to be sprayed out as an aerosol. And as it sprays out, it cools because of its expansion and then hardens into whatever shape you're blowing it into. Guess how they would propel these styrofoam particles into aerosol? They would use extremely high pressures of CFCs. So, kind of like how the ice core data shows these, right, kind of crunching of the ice and trapping gas inside of it, when this styrofoam container was quote unquote freezing or hardening, it would trap within the matrix of all those particles little bits of CFCs. So, the theory was when you crunch up your styrofoam, all those CFCs go flying out into the atmosphere. So the point essentially is that's not supposed to happen, right? That's not biomass burning. That's not a plant. This is, right, what is it? Big Macs, billions and billions of these have been served, right? So there's hundreds of millions of little tiny instances of CFCs being distributed pretty much all over the place that aren't supposed to be there and that are eventually now getting emitted into the atmosphere. And I'm not blaming this woman particularly, but this was another application that the chemical companies were applying these CFCs to. They would be for propellants and aerosol spray cans. Obviously, one of the things was everybody had a lot of hairspray back in the 50s and 60s, and they had to do it up, and they would use a lot of hairspray. Not just that, right? Spray paint, and a lot of things are, right, involving, right, just disseminating aerosol kinds of spray paint cans. So again, the reason why these are good chemicals for that is because they're extremely cheap and they have very high vapor pressures. And again, you would understand high vapor pressure means lots of the gas builds up and helps make a pressure difference, right? You don't want to have to spend a ton of money if you want to sell somebody a bunch of Aquanet. You don't want to have to spend hundreds of dollars on that because the chemical inside that makes it come out when you push down on the nozzle, you don't want that to be an extremely expensive chemical because you want to sell millions and millions of units to Mrs. Moskowitz here, right? So the point essentially is there's all these little tiny instances now being disseminated all over the place that are producing CFCs. CFCs were also in refrigerators, freons, essentially, were the particles there. So those are the three major areas where now there's this flood of chlorofluorocarbons. Who cares about that? Well, chlorofluorocarbons are named because they're full of chlorine and fluorine as well, right? So here are the popular two that DuPont and Merck, the two chemical companies, the kind of giants at the time, were using, right? They would use something called CFC11 and CFC12. Now, Merck and DuPont came up with these kind of not so cryptic names for their molecules. The 11 and 12 were some convoluted formula for how many carbons there were, plus the amount of hydrogens minus one. It was this really weird way to name it, but essentially CFC11 and CFC12 were the molecules you see here, which, in terms of chlorine, they're loaded. Look at this. CFC11's got 3 Cl sitting there. CFC12 has 2 different chlorines. So again, why is this a big deal? Well, there's a certain amount of chlorine which is supposed to be there based upon these natural sources. These don't happen all the time. Obviously, plants are growing in seasons, so that's one we can't really, right, get a control over. But now we've got all these people all over the place using CFCs every day, and that's obviously going to change the balance of at least the amount of chlorine which is in the atmosphere, or at least that's what this man believes. So this is the first person that I kind of got excited by in terms of, right, atmospheric chemistry. His name is F. Sherwood Rowland. If you ever go to UCI, there's Rowland Hall, which is named after him for reasons which will be clear in a little bit. He looked like this back in the 70s. Kind of looks like pretty cool, like kind of like Wolverine almost with the mutton chops there. And this is what he looked like when I met him. So when I went to UCI, I was kind of a wide-eyed kid, and I don't know what I was going to do. And one of the things you do when you're going to grad school is you have to pick someone to work for. You have to pick what's called principal investigator, and you kind of go on interviews with a lot of the professors there, and I had an interview with him for a while. So very, very interesting man. And again, you'll see kind of why he's a folk hero in atmospheric chemistry in a second. But anyway, he comes from the tree of Frank Willard Libby, which you might remember is somebody that I'm pretending, or at least kind of have adopted as great grandpa. So this is grandpa in terms of my research objects. And then, right, we can trace him back, as we saw, to Guy Lussac for gas phase chemistry. The point is, Rowland was doing a bunch of work with radiation. He was doing radiochemistry with various kinds of isotopes. He would actually drive back and forth from UCI to the San Onofre reactor down there kind of almost to San Diego, which they've closed. And he would always tell stories about how he would have to drive back from San Onofre with all his samples in the back seat. And I don't know if you've done that drive before, but there's the border check there, kind of a little bit north of San Onofre. And so he'd have to kind of pass through there, and every now and then they'd stop him and ask him, what's that all about? And he would kind of try to explain it to him, and they would just go, moving on. They don't want to get into it with him about what's in his back seat. So anyway, he got a grant to go to Austria to watch a conference, and at this conference, there was a talk by a guy named James Lovelock, which I'm sure you've never heard of, but James Lovelock is kind of considered the first environmentalist. He was the first person to think about how are we able to conserve, how are we able to think about the Earth more scientifically versus, right, oh, free the bees and I don't want to pollute and no nukes, that kind of thing. It was more like scientifically, how can we apply our scientific knowledge to the idea of trying to help the Earth be more healthy, essentially. So, of course, he's an interesting dude. He had a whole bunch of projects he was involved in. One of the projects he was involved in was with a ship he called the R.R. Shackleton. And the R.R. Shackleton was basically a yacht that he kind of hollowed out and put a bunch of scientific instruments on. This is him up here in the corner. And on there, he put a bunch of things that could analyze gases and kind of figure out what's kind of going on. So I don't know if he was just on vacation and decided, hey, I might do this, but he basically sailed around the world, or at least around a lot of the northern and southern hemispheric seas. And while he was there, took air samples. And he gave a talk that Dr. Rowland was at, where he was saying, here's what I saw for my air samples. And the thing that got Dr. Rowland excited, or at least probably not excited is the word, but maybe freaked out to be a better word, were two plots that he put up about his distribution he saw of CFCs all across the globe. So here's a plot over here showing 0 for where obviously the equator is, and here's the northern hemisphere, and there's the southern hemisphere. And there's two curves on here. Again, here's basically concentration over there, and we have CCl3F, which is CFC11, and this is then CCl4, another one of the CFCs that was being used. The point of this curve and this curve, also another curve showing a different plot, where we have, again, 0, northern hemisphere and southern hemisphere, is there's obviously an elevated amount of these particles in the northern hemisphere, because that's kind of where most people live, right? Most people live in Europe, and they live in the Americas, and they live kind of in the, right, in Asia. It's kind of a northern hemisphere portion. Southern hemisphere, not as many people, so there's not as many places where these CFCs may be coming from. What got Dr. Rowland and, of course, Lovelock interested was that they were seeing non-zero concentrations of those particles over not populated areas. So what's the point? The point is these CFCs, when they're emitted by people living in Europe in the northern hemisphere, they don't react with anything, right? If they would react with something, you wouldn't see them over Uruguay. They wouldn't be out there because they would have reacted with something in the atmosphere on the way to trying to get to Uruguay as they mix in the troposphere, and they would have a short lifetime. The point is, this, of course, purposely is an inert gas, as you see. It's not reacting with anything. And the other thing is, this was a talk he saw in 1971 or 1972. DuPont has estimated that they are using the most of these CFCs they ever have since 1960. Now remember, 1930 or so is when these first were starting to be used for industrial purposes. So there's almost now 40 years of different types of applications where these CFCs have been put out constantly into the atmosphere. This data set is showing the CFCs are not going to react with anything. And Dr. Rowland goes, right, because that means there's no sink for these particles. These particles are going to eventually be not reacting with anything and going into the stratosphere, which Dr. Rowland says that's going to cause a problem for the chlorine balance. So I'm going to spoil a little bit. You might or might already know about the CFC story. It does eventually result in a Nobel Prize. These are the notes that start off that research. This little cocktail napkin here, These are Nobel Prize winning notes that you're looking at, which are notes that looks like you and I could draw down. So I guess, again, that's a little bit of this idea. It doesn't take much to change the world overall. So these are notes that you'll see eventually lead to an extremely, extremely important scientific discovery and eventual success. So I'm going to give Surprise Kid his due here because, of course, we're all shitting our pants at this point. Okay, so CFCs don't go anywhere. They get into the atmosphere. They essentially now move around, and this data set shows they will get into the stratosphere. Is that a problem? Because remember, the thing that makes ozone go away, when we talk about these ozone hunters, is Cl atoms, right? The radical. So that's a big problem if somehow CFCs will go into the atmosphere, cause Cl radicals to go up. Again, they're inert, so maybe they get up there and just kind of, right, float around and float away and never come back. Of course, that's a different problem for, right, maybe Mars or something, right? The point essentially is there an issue that these molecules are going to pose to the ozone layer? We figured out they're going to get there. So Dr. Rowland calls up his buddy Mario Molina, who again has some pretty tight face lettuce going on, nice beard there. Here's what he looked like when I met him. He's over here on the far right side. This is the person that was my one of my principal investigators in graduate school. So this is some dude, I don't know who that is. But these are the three people that are sort of right in my academic tree. These people get together and say, is there going to be a reaction we need to worry about between light and these eventual CFC molecules? So Mario J. Molina studies then the relative photolysis rates and photolysis ability of CFCs, and he finds out, you know what, if we do get light below 220, pretty high energy light, but if we get to that wavelength, the CFC11 and CFC12 right here, they're going to eventually break apart and produce chlorine radicals, which of course is an issue, right? The chlorine radical is a problem because that's going to upset the balance of the Cl plus O3 ozone depletion cycle. But remember, this might not be a problem if there's a low quantum yield for this, right? The quantum yield is low for this, then who cares, right? That's not going to cause a big enough difference. So the last part we needed to figure out then is what's the quantum yield for these. So let's see if it's got a low quantum. Oh no, the quantum yield is 1, right? So this result, this reaction set right here, it's showing that every single molecule that's been emitted by Mrs. Moskowitz and me as a little tiny 5-year-old eating my Big Mac and all the people that have done anything with the freons, right, the refrigerator breaking and having the CFCs escape out into the atmosphere, every single one of those little CFC molecules is either already up there or slowly making their way up to the stratosphere. Once they get there, they're going to break apart into Cl, and as Hudson says in Aliens, it's game over, man. CFCs are going to have a big, big impact on the health of the ozone layer. So these guys start telling everybody they can about how, hey, CFCs, it's a bad story. There's a real big problem with this. Remember, Rowland learned about this idea in 1971, maybe 1972. They probably needed a couple months or maybe even a year to make sure their data was good. They really did have this relationship between the CFCs, the light that they were going to be absorbing, and the quantum yield for it. So let's bake in there a year of writing up papers, getting it published and all that. 3 years, maybe, maximum they had before CFCs are actually banned in California. Think about that for a second. If you said to somebody, hey, I want to get something banned because I've got this great research that shows the world basically could be ending because of what I'm finding out, how hard would it be now in 2020 to get anybody to change their mind about anything, let alone, as you can see here, 2 years after that, have America make a right national decision that everybody gets behind? I mean, it's unthinkable over the last 10 years about sort of how crazy our politics system has become. Again, I don't want to get political. I want you to see this is a very, very important result, that science, good science, was able to change pretty much everybody's mind about this, right? I guess, as you probably already know, CFCs were banned in America. They were banned worldwide later because of the research we saw here. And as I kind of spoiled, the team involved in this project, Dr. Rowland, of course, being a very big member of that, the team was awarded the Nobel Prize 21 years after they published their original findings about this. And of course, changed the course of stratospheric chemistry for sure, and probably, as you'll see a little bit of coming up, maybe the ability of us to be living as we are right now, right? So again, this is an extremely important idea. So I don't know if you know this about the Nobel Prize, but there's a big party. You go to meet the King of Sweden, or at least this is what he did in 1995. So there's Dr. Rowland shaking hands with the King of Sweden. There's a big, huge dinner with a bunch of people at it. I like to pretend like this is me right there, but I didn't go. I wasn't even part of this research at that point, so I don't have any Nobel Prize winning share or portion of it. And when, of course, you become a scientist with a Nobel Prize in your belt, you get to rub elbows with very important people. So you might be too young to recognize all these people. Of course, there's Dr. Rowland. This is Al Gore, which you might know as Man, Bear, Pig, Man. And also you might have heard of the movie, right, The Inconvenient Truth. This is kind of where I always kind of think maybe even this day, Al Gore looks as if he's like, oh, interesting. This is a big deal. Maybe I could make a movie about this in 15 or so years. And you might recognize this guy here. Here's Bill Clinton. He just looks miserable. Doesn't he? Just looks like he's thinking of anything else besides what's happening around him. So there's kind of the overall story about Dr. Rowland and where he kind of, right, gets his notoriety and his fame. And the point I wanted to get from this is that science can do it. Science can make an impact. And I don't know, your generation, of course, gets a lot of flack for being millennials and being lazy and whatever, and having a different attitude about life. But this is what can happen. Science can survive. Science, the good science at least, can actually make things happen. So that's kind of what, at least this side of the discussion, right? It's trying to pump you up a little bit. Okay, to finish up, I wanted to talk then about the idea of the health of the ozone layer, right? Because like I said, this overall discussion doesn't really happen much anymore. And there's a reason why, and the reason, of course, is because CFCs were banned, and right, we don't do that kind of stuff, or at least we do other less damaging to the ozone layer, at least versions of those kinds of CFC molecules. But because of the interest, again, it's flashback to 1971, 1972, flashback, we want to make sure that, right, the banning of this or the continued, right, pouring of these CFCs that are going to, in 1972, there still are 40 years or so of these particles that are going to make their way to the stratosphere. I failed to mention this, but the idea was that those particles have about 25 or 30 years of life they live in the troposphere before they actually get to the stratosphere, right? So the point was we wanted to see what's the damage going to be, right? So in 1975 or 76, they started building research posts out in remote areas where they could measure the ozone layer very efficiently. And one of the places they built it out was in McMurdo Station, which is this thing here. It's basically the South Pole Observatory. There's all kinds of cool stuff that happens there. I actually had a couple friends that spent some time there. They said there's a lot of drinking and a lot of poker when you go to the South Pole Observatory because there's just basically nothing to do. It's too cold outside to do anything. And when it is not cold outside, it's not cold outside for, like 6 minutes or whatever. So I guess you drink a lot and play a lot of poker if you're at the South Pole Observatory. But among other things, they monitor the health of the ozone layer. And one of the things they do to do that is do what's called a balloon-borne ozone sonde. An ozone sonde is a little tiny machine that has a little, for lack of a better phrase, little sniffer that essentially sniffs the air, runs it through a tiny little solution of potassium iodide, and this little redox reaction happens. So the ozone molecule reacts with I- and eventually gets reduced, the I- gets oxidized into this iodate molecule. And of course, we have this reduction of the O as it reacts with the I-. So little potential between there, little voltage creates around there, and this little balloon-borne thing. So the ozone sonde itself is that bit. This is a weather balloon that goes up and eventually breaks, and this thing then falls back down. They go grab the data that it was taking. So basically it takes every so often a little sniff of the air, pumps it through, and measures the potential for the reaction. The potential it gets, the voltage it gets based upon the amount of O3 that's there and the amount of O2 it's producing, it translates that into the partial pressure of the ozone that's there. So of course we have these profiles then as high as the balloon can get before the balloon breaks, the profile of the ozone layer, essentially. This is what typical data will look like for one of these balloon-borne ozone sondes. Here we have on the left the altitude that the balloon goes up before it eventually stops giving us data or the data are no longer interesting. And of course on the bottom is the ozone partial pressure. which you could, of course, understand the more partial pressure, the more ozone there must be. Here is the very latest one I could find on this website right here. So it's basically a NOAA website that shows all of the data they've got from around 1975 until today. They go up about every 2 weeks depending on the kind of year, and as you'll see, it's the maybe interesting things that are happening. But under regular type of conditions, this is from a couple weeks ago, so April 25th, 2020, they sent the balloon up, and the balloon was like, good, 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 gave us a bunch of data here, and eventually shows that there's this nice healthy amount of ozone around 20 or so kilometers up. It's a little lower, obviously, at the South Pole because of the air being relatively cold, is compressed, so you have this relatively low height for the ozone layer, but again, nice big bulge in terms of the ozone concentration, showing you nice healthy ozone layer there. Again, a couple weeks ago is what this data set is showing you. Over here is the temperature profile. Again, you can kind of see it's decreasing somewhat. It's a little cold there overall, but that's the relative temperature profile you might be expecting for the troposphere against the stratosphere. Here is a plot from October 9th, 2019. So right before we were kind of getting ready for Halloween and all that, the South Pole ozone sonde shows, okay, nothing. Absolutely zero ozone at the exact same area where our data set from last week is showing nice, healthy ozone layer. So these balloon-borne ozone sounds repeatedly, ever since they started doing this in around 1977, 1978, they have constantly noticed this exact same thing happening in the October months, right? The ozone layer completely disappears above the Antarctic continent, right? The South Pole shows what you probably have heard of is called the ozone hole, right? So the ozone hole was discovered mostly because we were like, oh no, the CFCs, we better monitor what goes on with the ozone layer over the next few years. So we've continued to do this because we want to see how the overall health of the ozone layer is kind of being tied to what happens on the Earth's surface. So last thing we'll talk about then is, why does that happen, right? You can't just sew it up, as Boromir obviously is saying about here, right? We can't just simply sew it up because there's a lot of very complex things that are occurring in order for this to be forming. So that'll be our last little thing for this extra credit lecture. Why does that happen? And specifically, why does it completely disappear in late September and then basically the ozone layer reappears a little bit after December, January, and into February? How come that happens? In a very, very simple picture. Again, there are a lot of complex things that are happening simultaneously. It turns out there are three major reasons. Two of them are because of what's happening at the South Pole, and one of them is because of us, because of the CFC thing. So let's start off with one thing which is not really something we can avoid. It's called the polar vortex. So one of the things which is unique about the South Pole is every time South Polar winter begins, which again is about when our summer begins, the air of course gets very cold, and the air getting very, very cold, it starts to collect together, right? The compression of the air, because of getting colder, its density goes up. It's going to have a smaller volume. It's going to compress because of less energy there, and you get something called a polar vortex. Here's a very complicated looking picture of this. I kind of like to think about this as the South Pole is this big ice cube which makes all the air around there cold. There's not a lot of light, right? There's very little sun overall because of the tilt of the Earth now pointing this away from the sun. So there's an isolated bunch of air. They call it an air mass. That's a very fancy word in meteorology. There's an air mass which kind of floats above the South Pole, and it's stagnant, meaning it doesn't move around very much. So it ends up having, for the most part, the same kind of air basically in the same area. To borrow a phrase from topical conditions, it's quarantined for the most part, right? The air gets quarantined there because other air is basically moving away from it because that's hotter air, so it's freely moving, but it ends up in this vortex. The temperature gets extremely cold there, and we end up with a big bunch of quarantined, isolated air above this. So that's the first thing that happens, is there's a polar vortex that forms every single Antarctic winter, which again starts a little bit before May and June, right? For us, at least, that's when our summer is, that's when their winter is going to be. And we end up with this very isolated air mass that happens to be over the South Pole or over the Antarctic continent. Now, there's a hilarious movie which actually has been on HBO quite a lot the last year or so. I think, of course, because of the increasing interest in climate science, which is called The Day After Tomorrow. Now, if you haven't watched this movie, have some drinks, have some legal chemicals, let's say, and just watch this and make fun of it. I won't spoil it if you haven't seen it, but there's a polar vortex that plays a very large part of it. It's kind of like the antagonist of the movie. It's got Jake Gyllenhaal running around the streets of New York. You can see, of course, the results of the polar vortex here. And they're running and running. They're running from the vortex. They're slamming doors on the vortex. They're jumping into fires because of the vortex. It's hilarious. It's a hilarious movie and has a very, very interesting sociological statement to make at the end. So again, after the final is over and you've got a few free hours, please fire up this movie if you haven't yet. It's hilarious. It was probably the best movie experience I've ever had when I went with a bunch of my graduate school friends in atmospheric chemistry to watch a movie where they completely get everything wrong about climate science. But anyway, it's pretty funny overall to think about this in terms of the polar vortex kind of happening. We also kind of coincidentally had a polar vortex this weekend, which is, I guess, wreaking some havoc in the Northwest, There's record colds because of a really very, very cold air mass, which has moved around kind of all throughout the Northeast and Midwest. So polar vortex is one thing that happens. The punchline is this keeps a very similar amount of air stagnant, hanging out, not able to escape out of this vortex. Next up was our fault, Again, we kind of talked about there at the beginning of this, Ozone is very sensitive to the amount of ozone-depleting chemicals that you might throw at it. And I spent a little time just now talking to you about where CFCs have made a play. Remember, CFCs in 1930, 1940, 1950, 1960 were put out by pretty much anybody, anywhere. And they have been slowly, over the course of the last few decades, we're now talking about 1972, moving up into the atmosphere, getting into the stratosphere, and as Dr. Rowland and Molina showed, those will produce chlorine radicals. Those chlorine radicals will, of course, find their way in to this polar vortex. Now, here's the other thing that happens, The Cl atoms that are in there, they like to react with anything. Now, again, we said they like to seemingly move other molecules out of the way to react with ozone, but they could also react with, here you can see what's called a methane reaction, or also the one of the products of the ClO3 reaction is ClO. And ClO here you're seeing is reacting with NO2. So there are two molecules that are out there in the stratosphere that are called reservoir species for chlorine atom, So HCl vapor, and this thing here is called chlorine nitrate, chlorine nitrate, That's this one here. Those are two particles where the chlorine kind of stops reacting with stuff. So it kind of sequesters it, puts it in timeout, let's say, So the Cl, or a residue of the ClO3 reaction, ClO, these are two reactions which essentially stop the chlorine from going after ozone as efficiently as it normally does. So whenever these are elevated in an air sample, that represents the chlorine is no longer able to deplete ozone. The problem is it's so cold in the stratosphere that all the water that's around is going to freeze, and it freezes into very, very fine ice crystals called polar stratospheric clouds, which is basically floating snow, Very, very fine crystals. The crystals allow for surfaces of ice to form that weirdo reactions happen, The reactions that we expect are normally gas phase reactions. Again, what I'm talking about is the chlorine-related reactions. We know all about what the chlorine does in the atmosphere, It likes to react with ozone or with methane or with NO2, which will produce these reservoir species. Here's the problem, Those two reservoir species, chlorine nitrate, which is right here, and HCl, which is right here, they can react on these ice surfaces which are present within the polar vortex, and they form kinds of molecules that don't normally form, Again, the molecules we're getting here, either Cl2 or chlorine nitrite, those are two chlorine molecules that normally don't happen. There are no sources of chlorine gas, literally Cl2, or chlorine nitrite. Those two kind of molecules normally don't get produced unless you have the reservoir species of chlorine, chlorine nitrite or chlorine nitrate and HCl, and super cold temperatures to make these ice surfaces. So we have now these heterogeneous reactions that are occurring, and what are they making? They're making activatable chlorine. They're making chlorine particles that theoretically have a potential to react with ozone. This wouldn't be so bad unless there was a crap ton of chlorine in the atmosphere that we put there, right? That's what made this happen in terms of, right, how bad it's going to be in some of the results. It's because of the sheer amount of chlorine which is present in the atmosphere from all the CFCs that we've done. Again, these reactions would happen regardless of CFCs, but they're happening to produce way more chlorine containing compounds than should be there. That's what the human influence has been on the ozone layer being depleted, specifically here in the polar vortex. And then lastly, there's then the concept of the sunrise for the Antarctic continent. Now, before we move on, this would then be the other thing that I might be asking about. So come out of your coma for a quick second. If you are wondering what's the other question going to be, the question might be, what are the 3 dominoes, according to the lecture, that happen simultaneously in order for us to see a south polar ozone hole? So, of course, it's the polar vortex forms. You could say then heterogeneous reactions create activating chlorine or something that involves what it says there for number 2, and then, of course, the polar sunrise. So those are the 3 things that are occurring. So the question you're going to get on the final will be something about what are the 3 things that occur according to the lecture that build the ozone hole. All right, so with that said, polar sunrise comes out. Now again, I kind of mentioned this about the polar vortex, right? There's no sun for a large amount of time because of the nature of what's going on for the tilt of the Earth, right? Here's kind of a weird looking plot. I don't know if you can make that out, but it says over here, right, it tells you what time of day it is. So there's midnight, and then there's midnight the next day. Here's the relative time of the year we're at. So, of course, the month of the year. And then this gives you these sort of weirdly defined versions of being daylight or not. So, of course, here it's day all the time because that's the South Polar summer where there's lots of sun basically all the time. And then, of course, here is where there's the South Polar winter where there's no sun. You compare this to not the South Pole. This is Kingston in South Africa. You see essentially there's some daylight and some sunlight every day. So you have then the cycling of the temperature a little easier because the sun comes out and comes down, and so you can variate the temperature a lot easier, right? The point essentially is the temperature is going to be constant all day, either warm enough because of sun coming out or super cold because the sun doesn't come out. So what this polar sunrise is all through these times here, right? Again, March, April, May, when we have summer, they have winter, there's no sun at all. So the polar vortex forms around, right, March, April, and May, and now all those crazy chemical reactions of the trapped chlorine compounds start building up all that Cl2, all that chlorine nitrite, that's all being built up through June, July, and August. And kind of around here, right, August or September, the sun comes out and we end up now bathing all these trapped compounds with photons. So polar sunrise then kicks off the possibility of chlorine getting reactivated in order for it to start going after ozone molecules. Last thing that happens, of course, is because of this ozone, right? The chlorine species, which we said here were, right, the non-reservoir funky versions of the chlorine particles, Cl2, straight up chlorine gas, doesn't sound very good overall. And then this one, chlorine nitrite, those have relatively low energies required, right? The wavelength for this is high. Of course, it's still in the UV, but there's plenty of this kind of light passing through the stratosphere, which is where the polar vortex is, right? That's again where this vortex is happening all throughout the entire atmosphere there. There's plenty of Cl2 and ClNO2 kind of sitting there waiting for something to happen. And the minute the sun comes back out, boom, it's Christmas. Cl all over the place. The piñata explodes and num, 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 num. Those Cl particles with a photolysis yield of 1 destroy all the ozone. A whole bunch of Rambos come out with Bowie knives and M16s and just start going to town on all the ozone around it. In fact, here is a data set that was shown to Ronald Reagan in 1987 because DuPont and Merck were like, oh, we think we should be able to make some chemicals again and lobby, and money. And the climate scientists were like, dude, look at this. Let me just show you what's going on. This blue graph shows the ozone layer, essentially. So this is going from left to right. You're walking toward the South Pole. The minute you hit the South Pole area, it dives to 0. Guess why? The CLO particles go up exactly with it. It's a lot like that climate, the temperature curve, right? The point is CLO is low when O3 is high, and CLO is high when O3 is low. I wonder why that is. Maybe it's because all the Cl that we have in there is Ramboing the crap out of all the ozone particles, converting those CLs into CLOs, and the O2 or the O3s, of course, into not ozone. So this data set was shown to Ronald Reagan, and he was like, oh, I see, we probably should not then allow any more chemicals to be produced. So that essentially is proof positive. We have this definite relationship between the ozone hole and the chlorine that's producing it. So again, it's not all our fault that the ozone hole forms, but it's a lot our fault that the ozone layer was in dire straits for 40 or 50 years because of us putting out all these CFCs that eventually we're going to go almost one-to-one with an ozone molecule. So how bad did it ever get, right? So every year they show what the relative ozone hole looked like. Remember, these little plots here show where the blue is very low ozone and the red and green are healthy ozone layers. You can see the very first ozone hole discovered was again in 1979 when they're like, oh, hey, we should probably monitor what's happening out there. These are satellite pictures, which are all kind of stitched together to give you a matrix of the relative picture. You can see here in 1979, there's a bunch of red out there, nice, a lot, tons of ozone, and there's a very small little lowering of the ozone concentration, sort of centered around, right, the Antarctic shelf. Look at what happens about 10 years later. Big hole. What about 10 years later? Big hole. 2011 was on record the biggest ozone hole there was. Biggest, of course, meaning the widest it got and also the lowest concentration there was. Now, normally, if the ozone hole, let's say the ozone hole happens all the time, nobody cares because nobody lives out here. But look at this, right? This got really close to where people are living. And if people live under no ozone, as before we saw, there's going to be a lot of overall problems. So this was the picture we have from up until 2011. This is the picture from October 2019. This is again when the ozone hole is the biggest it ever gets for the year. Now I've been doing this lecture for about 7 years now, and this is I'm not going to hype it up, but this is the most red I've ever seen on one of these plots when I show what's going on for the ozone hole of the time, right? So again, we still have one. We still have a pretty damaging hole right there, but like I said, this is much, much more improved. Just real quickly, look at what's going on here, right? There's barely any red out there, right? Again, there's red out there, but it's mostly green in our hole from recently, showing a lot of repair happening. So again, what's the point of this whole discussion? The point is what you do scientifically, it can make a difference. If you are passionate about it, if you tell the right people about it, and if you have good science, you can make a difference. And I think that's why a lot of you guys are in this class or in this major or in this path, is you have this desire to make a difference for better. And this is the point, is that it actually can happen, right? It's going to get better every single year because of us in the 70s going, knock it off with that crap. It's not good for the environment. And we are showing that our decisions that we make can definitely have an effect on the overall, at least here, health of the atmosphere, but also the health of everybody involved. Okay, so the short assignment I'd like you to complete to wrap up this first part of the extra credit. I always want to take the temperature of the generation of the time. So it's always interesting for me to kind of see what you're worried about. So I'd like you to write a little quick, you could be half a paragraph or a few lines about answer to this question. What concerns you about the most in terms of the future of life on Earth? There's no wrong answer here. You can write down whatever you think it is that scares you or you are concerned about the most. Whenever you think about what's the problem going to be that we need to solve, what is it that's going to cause the most damage? What is it that's going to bring us down as a human race? What is it that we have the biggest worry about? I think I'm going to take COVID-19 off the table because that's too easy of an answer. So pretend like COVID-19 isn't something that you're probably concerned about every day, although that's obviously something that we obviously are very, very concerned about. But I'd like to kind of think about what else besides that. So you can't say ozone depletion because that's solved, and even though you probably should say, a viral outbreak because that literally is what's happening right now, let's get a little more fresh results. So please don't say COVID-19 or a virus outbreak. Let's see what else we could think about, because we seem to be able to, although not as much fun, we seem to be surviving it generally as a race. We seem to be getting through that. So that's what I'd like you to do. So I have the assignment link underneath the video link, so please submit that as a PDF, or if you can't get it to work, you can email it directly to me, or if you want to send me an email with what your answer was. So I'll add 1 point of extra credit to your score if you submit that to me by 7 p.m. tonight. Okay, and thank you for listening through the entire thing, and I always like to make the joke that I know you came in for the extra credit and for right getting the lab checkout done, but I like to kind of sort of pretend you watched this video because you were interested in what I might have had to say about this topic, and you just wanted one more time to listen to me blab on about stuff. So if that was the case, then I got you. All right. Thanks for watching. I will see you next week.